Yeah, welcome to Mathematics and new challenge. It's a Christmas challenge. Santa Claus, pixie easy, and a simple y equals mx plus b. Alright. Before I start, I should say, of course, you can download this document. The link is in the video description. Okay. So let's see. Santa Claus has a problem. For some strange reasons, he needs an approximation for the square root. He can remember from school the Babylonian method, but he does not like to iterate a couple of times to get a reasonable result. He also knows about the Taylor series, but he does not like to remember terms of higher order. All he wants is a simple y equals mx plus b. No parabolas, no hyperbolas, no crazy integral expressions. Santa Claus visits the pixie Easy, a close friend of him and a brilliant mathematician, and explains the situation. Pixie Easy takes pen and paper and has following suggestion. We should approximate the square root of x for x in the half open interval from n squared to n plus 1 squared for n greater or equal to 0 for every natural n in the following way. Let s of x be the approximation for square root of x positive and real. If x is near n squared, in other words, for n squared less than x less or equal to capital A of n, we take the function as 1 of x is x plus n squared over 2n for n greater 0. If x is near n plus 1 squared, in other words, if x is between bn and n plus 1 squared, we take as 3 of x is x plus n plus 1 quantity squared over 2n plus 1 for n greater or equal to 0. If x is far away of n squared and n plus 1 squared, in other words, if x is between an and bn, we take as 2 of x equals mx plus t. M and t are positive real numbers for n greater or equal to 0. And this line has two satisfying following properties. The first one, S2 of n squared minus n equals F2 S2 of n plus 1 quantity squared minus n plus 1. Here I should say S2 of n squared and S2 of n plus 1 quantity squared are defined for determining n. Okay? So n squared and n plus 1 squared is not in this interval, but for getting n, we can use this, okay? And the second property, t is the minimum over all b's of following expression, the integral from n squared up to n plus 1 quantity squared over square root of x minus nx plus b, and the whole integrand squared with respect to x, of course, we integrate, okay? So it's function squared and then integrate, okay? It's not integrate and then square. So first square, then integrate. Yeah, we minimize over b, and this is our t, okay? Perfect. Alright. Good. Can you quantify the amicability of this linearization? Asks Santa Claus. Sure. The cardinality of the interval an to bn is 2/3 of the interval n squared up to n plus 1 quantity squared. And this is valid for all n, even for the case 0. Beautiful, isn't it? So this was the conversation. And now let's call our three intervals j1 of n, j2 of n, j3 of n for s1, s2, s3 for the functions s1, s2, s3 respectively. And let c1, c2, c3 be the length of those intervals, so the cardinalities will be defined as by the cardinality of interval from a to b is b minus a. Okay? So show following. First, a. Like Pixie Easy already said, that c2 over the cardinality of n squared up to n plus 1 squared is 2/3 for all n greater or equal to 0. B. The cardinality of C1 and C2 are of the form 1 over x plus minus h of n, where h of n is approximately where h of n is of the form of a hyperbola 1 over n. Okay, this is enough. C. The absolute value of square root x minus s2 of x. This is bounded by 1 over 12 n plus 6. I guess this should be, we should be equal with that. Okay, we are fine. D. What is D? The integral from n squared up to n plus 1 quantity squared, square root x minus s2 of x dx is 0 for all n. E. What is E? If we calculate the intersection from s2 and the square root of x, we have that these two intersection points in x1 and x2, they are not rational for all n. And F. The cardinality of this interval from x1 up to x2, where x1 is smaller than x2, over the whole interval 2n plus 1 is square root 3 over 3. Yes, this is my Christmas challenge. Like I said, the document is in the video description. Have fun, enjoy, bye bye.